meter data, and I was just kind of cruising through some of the notebooks that people were using to get really high accuracy on that, and people were using this method called XGBoost, which is a variation of random forest, which we'll learn today. So classification is a little different than what we did yesterday. Yesterday we did linear regression, which predicted a continuous variable. But in the case of, say, Titanic, when we want to predict if someone's going to survive or not, that's not really a continuous variable. So yes, we can encode that as 0 or 1, but I'm going to show you why we can't use linear regression to predict a 0 or 1 type output. So we're in the section of machine learning, the second half of the data science process, and we're going to start by looking at classification versus regression. So here's another example of in regression, you might want to predict the percentage score that a student's going to make on a test. But the classification version of that will be if the student will pass or fail. All right, now we're going to start with logistic regression because it's a natural next step from the linear regression that you used yesterday. So logistic regression is used for 0 or 1 type predictions. And this is a little graph showing why we can't use linear regression. So here's an example. So we have some X feature that we're going to use to predict Y. And if we use linear regression like we used yesterday, we would fit a line to this data. It would fit something like this. But notice, this would make sense for, I guess it would kind of make sense between X being here and here, then all the numbers between here would be between 0 and 1, right? And we could kind of interpret it as a probability. But then when X becomes less than Y equaling 0, then what does that mean? It doesn't really have any meaning. And 0 and 1 can be, we can kind of encode that as whatever we want. Normally that's like true or false. So in the case of survived or not survived. And so we choose like what our 0 or 1 will be. But yeah, it wouldn't make sense to like predict less than not survived, right? So what we want to do is bend this line and create, this is what's called a sigmoid. You can think maybe sigmoid because it looks like an S, sigmoid. And the math behind this is what it's doing is it's saying that there's actually, it's still, in a weird way, it's actually still linear regression, but it's linear regression on a transformation of our original input features. And so let me show you what that is in an equation. So remember yesterday we used y hat equaling wx plus b. That was our model. So this is our new model. And this kind of math, this is like an exponential raised to our b plus wx over 1 plus b raised to our wx. And what that does is it transforms, it makes it so that line can become squiggly. But remember, a model is just an equation. And in this case, this is our equation. So when we do machine learning, when we fit the model, we're still finding our w and b, just the same as yesterday. It's just that w and b don't have the same type of relationship to y hat as they did before. So that way, say x is like age. X can be, and y hat would be survived or not survived. So age can be, as age gets lower, maybe there's a lesser chance to survive. And as A gets higher, there's a higher chance to survive. So remember yesterday we talked about 2 score functions. Pop quiz. I'm going to call on you. What was one of the score functions?
R squared.
R squared. That's good. And what? Can you tell me a little bit about R squared?
R squared is between 0 and 1, and the closer to 1, the higher correlation that it has.
Yeah, that's a great answer. And we talked about one other score function at the end. Tobias? Do you remember what it was? That's okay. Let's see, anyone else in here? I just kind of briefly mentioned it at the end. Remember, I'll give you a hint. At the end, we were trying to predict how much money, I think it was Rodney, was going to make from his customer. And we predicted it would be $4.47.
Root mean square.
Root mean squared error. Yeah, that's good. So, and remember it was around $1. So on average, we were about $1 off. So those are score functions. So the score function that we'll talk about for accuracy is, or for classification is accuracy. And maybe even the math would confuse you more than just your intuition about accuracy. Accuracy is the number of predictions you get correct, right? So the number of times that you predict that someone survived and they actually survived, then that counts as 1 for your accuracy. Or when you predict that someone didn't survive and they didn't survive, that counts for 1 as accuracy. But when you predict wrongly, that counts as like 0 for accuracy. And so then you sum up over all your predictions and you just average that. So we would expect accuracy to go between 0 and 1, right? And for a classification problem, remember last time we talked about how it's sometimes useful to think of like your baseline. If your machine learning algorithm wasn't learning at all, what would its baseline be? And for R squared, that was 0. That means that it just predicted like just the mean, right? For accuracy, if our machine learning was just randomly assigning survived or not survived to our data, and our data sets were, our classes were balanced, what would our like baseline accuracy be? If I closed my eyes and just said, you survive, you don't survive, you survive, you don't survive, what would I expect? Like 50%. Yeah. So when you fit your machine learning model, if you're getting worse than 50%, you should be concerned, and you should. That's kind of your baseline. And what we're going to talk about right now is what's binary classification, 0 or 1. But a lot of times you want to do multi-class classification. So if you have like 4 classes, then your baseline would be like 25%. So as you have more classes, your baseline gets lower and lower. So the notation here is, this is called like an indicator function. It's a 1, right? But see the subscript is y hat equals y. And so that means 1 if this is the case, and 0 otherwise. This is just some mathematical notation that's used sometimes. And so this is called an indicator. So we just sum all the times that we got the prediction correct, and then we divide it by our overall samples, or overall observations. And that gets us our mean accuracy, our mean number of correctness. So that's our accuracy. Last time we talked about mean squared error as our loss function. And so that's what created that bowl shape that we saw. And so if we plotted, this is the loss function for logistic regression, just for reference. Well, we're going to start by, this is like a pretty interactive lesson, just like last time. Let's see. So remember last time we were able to adjust the W and B to fit the line to the points. Well, we're going to do that here also. Now remember, this red line actually is the graph of, in the same way that that line in our dots was the graph of our equation, our model, this red line is just a graph of this function. So I just graphed that function, that's the red line. And so our W and B, we can play around with it, and that will change this red line. So let's dissect what's happening here. So in this example, we're looking at, say we're doing a project for Spotify, and they want to know how many months do we need to keep a customer so that they're locked into our service. So we might have data like this. Each point, each blue point is a customer. And so let's look at this customer in specific. So this customer has been using the service for let's just say they're about 6.5 months. And they did not leave the service. None of these customers left the service of Spotify. All of these customers are observations of customers who did leave the service. And so that's why they're at y equaling 1, and these are at y equaling 0. Now, in the x-axis, so if you look at this person used the service for also about 6.5 months, but they did lose the service. So what you can see here is we're not going to be able to give a definitive answer. We can't, for example, we might want to put the line here and tell our supervisor, well, it's 6 months. But even if we do that, we're going to get some people wrong, right? Because if we say anyone over 6 months will stay on our service, well, according to our past data, we'll get a lot of them right. But all of these points will be wrong, because according to our prediction, these people should have left the service, but they didn't. And we'll also get all of these people wrong, because according to our prediction, these people should have left the service, but they didn't. So the blue dots are our actual data, and then the red and green lines are our predictions. So in the same way that yesterday we had a straight line, and that was our prediction line, right? That we were trying to fit to the dots. This time we have a curvy red line, and that curvy red line is the prediction of probability. So that's that sigmoid function we talked about. And I'm going to move those around in a second. But see what this is saying right now. So with this W and B, these were just chosen arbitrarily, but with that combination of W and B, what we're saying is that, and this text shows, we're predicting that a user with more than 7.9 months using the service will stay. So the red line is the probability, that's the model we're trying to fit. And then the green line is a function of our red line. So the green line is just, it intersects the red line at 0.5. So if your boss was asking you, how long do we need to keep a customer before they stay on our service, they're asking for a definitive number, right? They don't want like a probability. So depending on the question that your boss asks, you can either answer with the red line or the green line. So if your boss asked, how long before do we need to keep the customer before they leave the service, you would give them where the green line is. That's the binary classification. But your boss could ask a slightly different question. They could say, if the user has used the service for 6 months, what's the probability that they'll leave the service? And that's where you would give them the red line, which maybe is like 0.1. That they'll stay on the service, it's 0.1. Now, we want to put this green line to, as best we can, in the dots so that it classifies the dots correctly. Because the green line is our prediction. And so right now we're correctly classifying all the people who left the service. But see, there's a lot of people that our green line doesn't match up with the actual data. So we want the green line to overlay our data as much as possible. And that means the green line is our predictions. That means the prediction matches the actual data. So if we move our W and B, let's see if I move the B, let's see what happened. Well, that's actually getting pretty good. One thing I didn't mention though. So moving back to here, see our accuracy is 0.64. So the accuracy, remember, is the percentage of data that we got correct. So you can kind of see we got about 0.64 of the dots correct, of the customers correct. So say there's 100 customers here that we're looking at, we correctly classified about 64 of them. But if I moved my B, let's see if I try to fit it, get a little bit higher accuracy. Okay, my accuracy went up a little bit, right? So now I'm correctly classifying 67 of my customers. And you can see that I've incorrectly classified these, I've incorrectly classified those, but I can't do that much better. You can play around with the W and B's yourself. Now kind of notice what happens when you change the W. Well, notice the red line, the red line can squeeze and spread out, and it can also change, so it can change like spread, but it can also change location, right? And so the red line can spread out, or it can shift left to right. And so the red line is what we're fitting, and the green line is just determined by the red line. The green line is always just wherever the red line is 0.5. That's where we draw the green line. So play around with that. A lot of this is really meant to play around with until you can convince yourself that you're kind of understanding what's happening.
So at the intersection of the green and the red line, are the people equally likely to leave or stay? Is that cross point?
It's where the probability is 0.5. Do you see that? So the green line always intersects the red line at probability 0.5. Because I think that matches our intuition too. If your boss was asking you, well, when will they leave? You would just give them, if you want to give them a quick answer, you just tell them any customer that has a better than 0.5 probability of leaving, you say, if you had to give them like a yes or no, you would say that that person left, right? Anyone with a greater than 0.5 probability of staying, you would say that that person stayed. That's like, if you want to give like a yes or no answer.
So is the red line the PDF of the sigmoid function?
Oh, PDF?
Right.
Well, this isn't a probability density function. Yesterday we dealt with distributions,
Right.
and PDFs and CDFs are the distribution functions.
So this is just the graph of the sigmoid.
Yes, of our logistic regression model. So just like yesterday, remember it was real easy to use an sklearn library. Yesterday we just imported linear regression and we just did linear regression.fit. Now we're just going to import logistic regression and we're just going to do logistic regression.fit. You can see I did pass a parameter in here. So one thing about sklearn is a lot of these models require a lot of what we call hyperparameters. They normally require us to set a lot of settings for the machine learning model. So if we were doing machine learning even like probably 5 years ago before sklearn, this class probably would have taken about 10 times longer because I'd have to go through and tell you how to set every one of those settings. It's still useful to know what those settings do because you can fine-tune your model and create better predictions and accuracy. But what sklearn did for us, which is really nice for people just starting out, is it set defaults for all of those. So that's why I can take away this argument and I can still run this, and sklearn will use what it thinks are the best parameters. So that's nice when starting out. A lot of these models might take like 15 or 20 parameters, and beforehand, before sklearn, we would have had to know how to set each of those parameters. But now we can kind of just let sklearn, at least at the beginning, take it. That's like a good place to start, and then as soon as we're like, okay, we understand what's going on, like we got a baseline, then you can start tweaking the parameters to get better accuracy. But I'm just going to include that for now. You don't have to know what that does, but you could include it or not. So I'm actually not even sure why I included it. I'm going to put that on notes. So again, we just do logistic regression.fit. I'm not sure if I mentioned this before, but I use, remember before we talked about features and target? So I use pretty interchangeably in my code. I'll use features as like capital X and target as my Y. That's like the more mathematical notation, whereas like features and target is the more like, I guess, coding or data science way to say it. But just know, anytime you see like capital X, those are my features. Anytime you see like lowercase y, that's my target. And as you're reading online tutorials and stuff, you should just know that because everyone uses something a little bit different. But yeah, so I fit with my X and Y. And remember yesterday, I showed you how you could get your coefficient and intercept. So I'm printing out my W and B. So up here, when we tried to pick like a decent W and B, we chose 1 and -5. And now we can see what the computer chooses. The computer chooses 0.9 and -4.7, so pretty good. But also notice that with the parameters the computer chose, we got 0.67 accuracy, the computer got 0.77 accuracy. And so obviously the computer did a little bit better than us. Now, again, how you can interpret the accuracy is, I'm not sure if there's 100 points here, but assume there are. That's saying it's correct. It's drawing the green line correctly through 77 of those 100 points, whereas we only drew it correctly through 67 of those 100 points. So that's what it's trying to maximize. Okay, math, which we don't need to do. So what I'm going to teach next is something called a contour plot. But to really understand that, see the correlation between this, what's going on here, what's going on here. So the idea here is take this and imagine, so it's 2D right here, right? Imagine taking this and turning it like this. So you're looking at the plot from the top. How are you going to represent that? Well, where the probability is very high, like up there, we're going to represent it with colors. And so I should put these maybe side by side, but that dark blue, so the darker blue, see how it gets darker blue over here? That means more probability of them staying. And see how that relates to when this line is higher, that's the more probability of them staying. And then when that line is lower, see how this gets more red? And that's the probability of them left. So again, it's like you take, like if this is the plot, going on, say this is the plot, take it and turn it on its side so you're looking at it from the top, and that's what you see here. So again, see how that green line's there? So imagine that green line being drawn there, and I take it and I flip it, that's where you see the green line drawn there. So that's like a contour plot, so it's just a different way to see that. And why is that important? Well, it's because of what's going to come next. And then also, so you see how we can pretty easily see the dots up here and the dots down there. Well, if I turned it this way, they'd all kind of look like the same dots. So I'm going to color the dots up there as blue and the dots down here as red. And so that's what you can see here. So all of these dots are colored blue and all of these are colored red. So that's another way to look at this classification. And so this might be overwhelming, but what I just want you to look at is this one right here. So what you saw up here was like a one-dimensional, we used only one feature. But what if we wanted to expand this to two features? Then we would get like a contour plot, like what you kind of see when you look at like a map of, you know, you're going hiking and you look at a contour plot of elevation. That's kind of like what we're looking at here. Yeah, so imagine this as like a mountain, a hill, and you want to look at that on the map. And so this is like when you go hiking or something, you see like colors, and that's like the contour here. It's kind of showing you like the probability elevation. And so, but a map is normally 2D, so see this is kind of 1D, it's only one dimension. So if we want to visualize like probabilities over a two-dimensional plane, this is like what it looks like. So I want you to look at this one. This is kind of what we've been dealing with. So you can imagine this is like the line, the curvy line, right, is going, so blue's low, so it's kind of like going low and then high. So it's like a, if you've ever been like hiking or you're looking at a map and you think of the color as the elevation, and the elevation being the probability. Okay, so decision trees. So
Before you
Yeah.
continue, are the numbers in the bottom right-hand corner, is that the accuracy? What's the,
oh yes, it is. Yeah, I'll come back to this plot. I just wanted to show that one, how to read this plot, given like what we were looking at. Any other questions on logistic regression? Okay, we won't actually be using logistic regression that much because it's just not a super powerful method. It's kind of a good baseline, but I don't personally use it in my own machine learning because there's more advanced models that I think are also easier to understand. But it's a good way to kind of see like probability and classification and how those two relate to each other. So, decision boundaries, we went over that. So decision trees, all right. So I have a video to explain decision trees because I think they do it really well.
Quest is growing down. StatQuest is growing. Hello, I'm Josh Starr, and welcome to StatQuest. Today we're going to be talking about decision trees. Here's a simple decision tree. If a person loves StatQuest theme songs, then that person is awesome. And if a person does not love StatQuest theme songs, then that person is slightly less than awesome. In general, a decision tree asks a question and then classifies the person based on the answer. It's no big deal. This decision tree is based on a yes-no question. But it is just as easy to build a tree from numeric data. If a person has a really high resting heart rate, then that person had better see a doctor. And if a person does not have a super high resting heart rate, then that person is doing okay. Here's one more simple decision tree. This decision tree is based on ranked data, where 1 is super hungry and 2 is moderately hungry. If a person is super hungry, they need to eat. And if a person is moderately hungry, they just need a snack. And if they are not hungry at all, then there's no need to eat. Note, the classification can be categories or numeric. In this case, we're using mouse weight to predict mouse size. Here's a more complicated decision tree. It combines numeric data with yes-no data. Notice that the cutoff for resting heart rate isn't always the same. In this case, it's 100 BPM on the left side and 120 BPM on the right side. And the order of questions on the left side, first about resting heart rate, then about eating donuts, doesn't have to be the same on the right side. On the right side, the question about donuts is asked first. Lastly, the final classifications can be repeated. For the most part, decision trees are pretty intuitive to work with. You start at the top and work your way down and down till you get to a point where you can't go any further, and that's how you classify a sample. Oh no, jargon alert! The very top of the tree is called the root node, or just the root. These are called internal nodes, or just nodes. Internal nodes have arrows pointing to them, and they have arrows pointing away from them. Lastly, these are called leaf nodes, or just leaves. Leaf nodes have arrows pointing to them, but there are no arrows pointing away from them. Now we are ready to talk about how to go from a raw table of data to a decision tree. In this example, we want to create a tree that uses chest pain, good blood circulation, and blocked artery status to predict whether or not a patient has heart disease. The first thing we want to know is whether chest pain, good blood circulation, or blocked arteries should be at the very top of our tree. We start by looking at how well chest pain alone predicts heart disease. Here's a little tree that only takes chest pain into account. The first patient does not have chest pain and does not have heart disease, and we keep track of that here. The second patient has chest pain and heart disease, and we keep track of that here. The third patient has chest pain but does not have heart disease. The fourth patient has chest pain and heart disease. Ultimately, we look at chest pain and heart disease for all 303 patients in this study. Now we do the exact same thing for good blood circulation. Lastly, we look at how blocked arteries separates the patients with and without heart disease. Since we don't know if this patient had blocked arteries or not, we'll skip it. However, there are alternatives that I'll discuss in a follow-up video. Remember, the goal is to decide whether chest pain, good blood circulation, or blocked arteries should be the first thing in our decision tree, aka the root node. So we looked at how well chest pain separated patients with and without heart disease. It did okay, but wasn't perfect. Most of the patients with heart disease ended up in this leaf node, and most of the patients without heart disease ended up in this leaf node. Then we looked at how well good blood circulation separated patients with and without heart disease. It wasn't perfect either. Lastly, we looked at how well blocked arteries separated patients with and without heart disease. Note, the total number of patients with heart disease is different for chest pain, good blood circulation, and blocked arteries because some patients had measurements for chest pain, but not for blocked arteries, etc. Oh no, it's another one of those ghastly jargon alerts. Because none of the leaf nodes are 100% yes heart disease or 100% no heart disease. They are all considered impure. To determine which separation is best, we need a way to measure and compare impurity. There are a bunch of ways to measure impurity, but I'm just going to focus on a very popular one called Gini. To be honest, I don't know why it's called Gini. I looked around on the internet and couldn't find anything. However, if you know, please put it in the comments below. I would love to know. Regardless, The good news is calculating Gini impurity is easy. Let's start by calculating Gini impurity for chest pain. For this leaf, the Gini impurity equals 1 minus the probability of yes squared minus the probability of no squared. Now let's plug in some numbers. The probability of yes equals 105 divided by the total number of people in this leaf node. And the probability of no equals 39 divided by the total number of people in this leaf node. After we've done the math, we get 0.395. That is to say, the Gini impurity for the leaf node on the left equals 0.395. Now let's calculate the Gini impurity for this leaf node, the one on the right. Just like before, it equals 1 minus the probability of yes squared minus the probability of no squared. And the probability of yes is 34 divided by the total number of people in this leaf node. And the probability of no equals 125 divided by the total number of people in this node. And if we do the math, we get 0.336. Now that we have measured the Gini impurity for both leaf nodes, we can calculate the total Gini impurity for using chest pain to separate patients with and without heart disease. Because this leaf node represents 144 patients, and this leaf node represents 159 patients, the leaf nodes do not represent the same number of patients. Thus, the total Gini impurity for using chest pain to separate patients with and without heart disease is the weighted average of the leaf node impurities. So to calculate the weighted average, we take the total number of people in the left leaf node and divide it by the total number of people in both leaf nodes. We then multiply that fraction by the Gini impurity for the left leaf node. Then we take the total number of people in the right leaf node, divided by the total number of people in both leaf nodes, and then multiply that fraction by the Gini impurity for the right leaf node. After we do the math, we get 0.364. Thus, the total Gini impurity for chest pain equals 0.364. And since I'm such a nice guy, I'm going to cut to the chase and tell you that the Gini impurity for good blood circulation equals 0.360. And the Gini impurity for blocked arteries equals 0.381. Good blood circulation has the lowest impurity. It separates patients with and without heart disease the best. So we will use it at the root of the tree. Note, when we divided all of the patients using good blood circulation, we ended up with impure leaf nodes. That is to say, each leaf contained a mixture of patients with and without heart disease. That means the 164 patients with and without heart disease that ended up in this leaf node are now in this node in the tree. And the 133 patients with and without heart disease that ended up in this leaf node are now in this node in the tree. Now we need to figure out how well chest pain and blocked arteries separate these 164 patients, 37 with heart disease and 127 without heart disease. Just like we did before, we separate these patients based on chest pain and then calculate the Gini impurity value. In this case, it's 0.3. And then we do the exact same thing for blocked arteries. Since blocked arteries has the lowest Gini impurity, we will use it at this node to separate patients. Here's the tree that we worked out so far. We started at the top by separating patients with good circulation. Then we used blocked arteries to separate patients on the left side of the tree. All we have left is chest pain, so first we'll see how well it separates these 49 patients, 24 with heart disease, and 25 without heart disease. Nice. Chest pain does a good job separating the patients. So these are the final leaf nodes on this branch of the tree. Now let's see what happens when we use chest pain to divide these 115 patients, 13 with heart disease and 102 without. Note, the vast majority of the patients in this node, 89%, don't have heart disease. Here's how chest pain divides these patients. Do these new leaves separate patients better than what we had before? Well, let's calculate the Gini impurity for it. In this case, it's 0.29. The Gini impurity for this node before using chest pain to separate patients is 0.2. The impurity is lower if we don't separate patients using chest pain. So we will make it a leaf node. Okay, at this point we've worked out the entire left side of the tree. Now we need to work out the right side of the tree. The good news is that we followed the exact same steps as we did on the left side. First, we calculate all the Gini impurity scores. Second, if the node itself has the lowest score, then there's no point in separating the patients anymore and it becomes a leaf node. Third, if separating the data results in an improvement, then pick the separation with the lowest impurity value. Hooray! We made a decision tree. So far, we've seen how to build a tree with yes-no questions at each step. But what if we have numeric data, like patient weight? Imagine if this were our data. How do we determine what's the best way to use to divide the patients? Step 1. Sort the patients by weight, lowest to highest. Step 2. Calculate the average weight for all adjacent patients. Step 3. Calculate the impurity values for each average weight. For example, we can calculate the impurity value for weights less than 167.5. Ultimately, we get 0.3 as the impurity value for this weight. And then we calculate the impurity values for the other weights as well. The lowest impurity occurs when we separate using weight less than 205. So this is the cutoff and the impurity value we would use when we compare weight to chest pain or blocked arteries. Now we've seen how to build a tree with yes-no questions at each step and numeric data like patient weight. Now let's talk about ranked data like rank my jokes on a scale of 1 to 4 and multiple choice data like which color do you like, red, blue, or green? Ranked data is similar to numeric data, except now we calculate impurity scores for all of the possible ranks. So if people could rank my jokes from 1 to 4, 4 being the funniest, we could calculate the following impurity scores. Joke rank less than or equal to 1, joke rank less than or equal to 2, and joke rank less than or equal to 3. Note, we don't have to calculate an impurity score for joke rank less than or equal to 4 because that would include everyone. When there are multiple choices, like color choice can be blue, green, or red, you calculate an impurity score for each one as well as each possible combination. For this example, with 3 colors, blue, green, and red, we get the following options. Color choice is blue, color choice is green, color choice is red, color choice is blue or green, color choice is blue or red, and lastly, color choice is green or red. Note, we don't have to calculate an impurity score for the color choice blue, green, or red, since that includes everyone. Bam! Now we know how to make and use decision trees. Tune in next time for random forests. That's when the fun really begins. Hooray! Oh,
All right. How was that? Good? Yeah. Random forests, I like them because they make sense to me. And they're pretty interpretable as well. And of course, because of sklearn, they're really easy to build. So, from a decision tree, or did you have any questions on that video?
Is random forest the same thing as a decision tree?
So a random forest is just a lot of decision trees.
Okay.
Forest, tree, yeah.
Gotcha.
Mm.
Gotcha.
Yeah. So, yeah, but let's build a random forest for a data set that we're used to, which is the iris data set. And I don't think we've built a model for the iris data set. So the nice thing about a decision tree, unlike the linear regression, remember the linear regression required a linear relationship between the variables. But sometimes there's a nonlinear relationship. Sometimes when something like passes a certain threshold, there's a nonlinear like jump to some other kind of relationship. And so decision trees are really good at capturing that. So if we load the iris data set and pretty much build a decision tree classifier, we can just fit it, and let's see what we get. Okay, so this is the decision tree that we got. So the nice thing about this model is we can print it out, and it's just as interpretable as like if we were drawing a decision tree ourselves for how we make a decision. The difference is that the computer gets to decide the kind of decision values to use. So up here they used pedal width. Okay, so let's look at what's in each of these boxes. So in the video examples, there's like a true or false, right? Like, is it needed? Had heart disease, right? Had heart disease. But you can use it for more than just a true or false. In this case, we had 3 species of flower, right? And so in the top, we have the value being 50, 50, 50. That means there's 50 species of each, 50 observations of each species. And so there's in total 150 samples. And the Gini. So something you didn't mention about the Gini is about like baselines. Remember with logistic regression we talked about a baseline of 0.5. So the Gini, if it's completely pure, then the Gini will be 0. So we want the Gini to be as low as possible. Maybe you got that from the video or maybe not. But if you have a binary classification and you have perfectly like 50 and 50, that's as impure as you can be, right? You have 50 of one sample and 50 of the other sample in the bin. In that case, your Gini would be 0.5. And so in the case of 3, it's 0.667. So there's an obvious relationship here. But see here, there's 50 and 50, so that's 0.5. And you can see how as we go down the tree, our Gini reduces. And so what the tree is going to try to do at each step is to get the lowest Gini possible. So up at the top, we have 50 of each, so that's the max Gini we can have. But we're going to remember how it goes through each feature and then chooses a threshold for each feature. And that's how it chooses at the top. It says, what feature can I use and what threshold can I use for that feature? They'll divide my data as best as possible. So it chose, is my pedal width less than 0.8? And so over here is, I don't like, so I think this arrow is like the true arrow and this arrow is the false arrow. Well, in the video it's the other way. Honestly, I don't really know. But let's just say that this is, the right arrow is going to be the true and the left is false. So all the samples that went over here would answer false to that question. So aka they have a pedal width greater than 0.8. And it so happens that, and this one doesn't show the species, but that was able to perfectly classify one of the species. So all species type 1, whatever that was, went into this bin. They all had a pedal width of
It's
greater.
got to be the other way around so that you can answer, any of them can answer.
So you think
the
it's
second-
true this way?
False.
You think it's false this way?
Yeah.
And true this way? I mean, you
Or
might be
they're
right.
less than, yes. Because if they're all less than 0.8, they can't be less than 1.575.
Oh, good point. a good point. Wait,
So I think it's true on the left.
true on the
Less
left.
than 0.8, true.
Wait, I think it would be true on the right. Because all the ones with petal width less than 0.8 go over here. And then we ask, well, is it less than 0.1?
Well, they all would. If they're less than 0.8, they're less than 1.75.
True. So all of these have. Oh yeah, I was reading that as 8. Yeah, you're right. Yep. Okay, nice. So yeah, this is false. Thank you. Yeah. So you're right. So this would be false. So everything over there is true. Now notice something. The genie is still not. Remember, we want a genie of 0. So this is perfect. So why don't we just keep going, building down in the tree, and keep like asking as many questions as we can until all of every observation is perfectly classified? Well, why did it not do that? Well, because we wrote max depth equals 2. See, we wrote max depth equals, and then you can set it here, but equals 2. So if I change this to max depth equals, say, 1, we'll be able to see it only goes 1 depth, or 2. So in the next lesson, we'll talk about why would you want to constrain it from being a perfect classifier. But for one thing, it's much easier to view, right? Than if we didn't add a max depth, we can try plotting it. I don't know, it might freak out. Okay, well, you can still read it in this case, but in a lot of cases, the tree just gets so big that you can't even read it. So remember last time so decision trees pretty much break your, so this is what we saw, the decision tree, but they pretty much break your feature space into like rectangles because they ask, so how you kind of view this is, right here, maybe like the first question is what is this, probability present? I don't really know what that means. But maybe the first question is asking is the start, well yeah, okay, the first question is the start greater than or equal to 8.5? And so that it draws that line, that rectangle. And so if the start is greater than that, so all of this data over here, then your probability is, actually just reading this for the first time, but see what it's doing is it asks these questions, and each time it asks a question, it partitions your feature space into rectangles, and so that every data that falls into that rectangle gets that classification. So remember last time we talked about how you can take pretty much like a topography like this and like flatten it by looking at it from the top. And so this is the top view of this plot. And so where it's really low, that's white. Where it's really high, that's black. And then this area that's kind of in between is gray. I don't know if you can see that there. But that's the way to look at the decision tree. So we can plot the decision boundaries. That's called a decision boundary. So in this case, petal width is less than or equal to 0.8. So you can look down here, and this is plotting the decision boundaries, and we can see petal width less than, what was it, 1.8 or 0.8? 0.8. So all the petal width less than 0.8 is this red region. And see how it perfectly classified all these samples? So if we look down here, in this rectangle, it's a little hard to see on the screen, but there's all these red dots down here, and those are all perfectly classified in that rectangle. And so all the points are perfectly classified in that rectangle, so that's why we didn't need to subdivide that rectangle anymore, because we perfectly classified all of those. But we needed to ask more questions for the yellow and blue points representing the other two species. So we asked, is the petal width less than 1.75? So this plot, so that's why you see now these two rectangles, because we did have that rectangle, but then we broke it into two so we could, that's where that question came from, 1.7 petal width less than 1.75. That's this line right here. So it created more rectangles to try to classify all the yellow points and try to put all the blue points in the blue rectangle. But you can see from this, there's some points that exist in the other rectangles, and so that's where you can see that the Gini values here, it didn't perfectly put all the points in the right rectangles. So this is a Titanic data set, and what we're doing here is you don't need to worry, I guess, about these few lines. Well, we're going to impute the age with the median age. We're going to define a target name and feature names, and then we're going to get our x and y, and then we're going to make a decision tree off of it. So let's look at what the decision tree is doing. That's maybe too much depth. Let's do 3 so we can kind of easily see what's going on. It's still rather large. Let's roll with it. So the first question, now we encoded male as 1 or 0. So 1 meaning it is male. So here it asks, is male less than 0.5? Meaning if it's less than 0.5, then that means male is 0, which means it's a female observation that we're looking at. So what we're seeing here is the Gini of this bin, and that Gini is 0.47 because it's very impure. There's a lot of people that survived and didn't survive in this. But I guess this first observation, this first entry in the list is the number of people who didn't survive or died on the Titanic. And so if we ask this box, if I ask this box, what class do you contain the most of, it would say the people that died. And so that's why it classifies everyone in this box. If I had to ask this one box, it would classify everyone died. But that's how we can get the most accuracy, right? If I just go on the Titanic and I randomly pick someone, I would have to say that they would die because that's a little bit more likely. But if we divide it by, well, if we ask it, well, were they male or female, then we can get better classifications. So being less than 0.5 means female, so over here. So now we can see that there's a lot more people who survived. And so there's a lot of females survived. And so if we had to ask this box, did the females survive or die, it would say, well, overall they survived. And you can see the Gini index. But we could continue to classify. So I can ask a few more questions. Well, okay, they're female, but are they third class? There's classes in the Titanic, so third class, second class, or first class. Third class will be 1 if they were third class, or 0 if they weren't third class. So this is saying, well, if they were third class, then we go over here, and we would say that they died. But if they weren't third class, meaning they're second or first class, then we would say that they survived. And we continue that way. So then we could be like, okay, well, they were third class, but let's look at the fare that they paid. So what's interesting there is it looks like if they, and you can continue like that. As you get like deeper and deeper, you get more kind of like weird predictions because now it's like trying to classify every data point individually, and so it becomes a little bit less interpretable. So again, that's why you might want to put max depth to something. Okay, so here's max depth here. So there's one more parameter I passed into here. It's min impurity decrease. So another way I can stop this tree from growing is by passing min impurity decrease. So what this is saying is, sure, it could split it again, but if that split doesn't help me that much, then just don't split it. And so that's what's happening here is, you see how this box decided not to split again. It's because what the computer did is it did, in the algorithm, it did split it, but then it's like, okay, actually, that doesn't help me that much, so I'm just going to not split it there. So it's another way you can stop the tree from growing. So what's fun here is you can play around with, you can predict survival with this box if you run it. And so I can check, okay, if I am not male, my probability, well, I can play all around with this. So first off, I can select male or not male. Okay, so if you look up at the tree, male being, if you're male, then you're more likely to die. And so you can play around with this, and you can see how by changing different parameters, your probability of surviving will change. And you can relate that to the tree. So you can see, you can play around with the parameters, and as you play around with them, track your settings here, and look at your settings here, and then follow that settings in the tree, and you'll see like what the tree did. Now how do you get, so it's predicting probability down here, right? How does it get probability? Well, it does a sort of averaging. So it will see, okay, how many times did I predict die or survive for this setting of person? And if I always predicted die, then my probability of dying will be 1. And so that's how we get probability out of this kind of tree. And now we get to an important part of the machine learning, that's the interpretability. And so that's like prediction, right? Like if you wanted to say if someone would die or survive, or the probability of dying or surviving, that is prediction. But the other part that's important to us is inference. What features are most important to someone's dying or surviving? And inference we talked about yesterday was like recruiting. And if you're doing recruiting, you might want to look at your feature importance once we fitted a model to see what was most important and who we decided to let on to into the company. And so you can get feature importance real easily from a lot of sklearn classifiers, but specifically decision trees. It's just dot feature importance. And so what you can see here is male is the most important feature for if they survived or not. I guess the second most is if they were third class. And then after that, how much they paid. And then the third would be what their age was. And the fourth would be if they had siblings or not. And you can kind of see that replicated in the tree. So how it gets these feature importances is it asks the tree, well, what was, right? So it put male at the top because that was the most important feature. If it had to choose just one, that's the one it would ask to be able to determine if someone survived or died. So that's how you get feature importance out of the tree. All right. Now there's something to be said for unbalanced classes. So as often is the case in, say, like cancer, if you're trying to predict if someone has cancer or not, that's a very unbalanced kind of problem because you might have a sample of 1 million people and maybe 100 of them will have cancer. And so you have this kind of class imbalance. So just a vanilla decision tree will treat all samples the same. But you might want to maximize for a kind of more balanced. You might want to punish the decision tree for misclassifying cancerous patients. Because say we only had 100 cancerous patients, well, our decision tree to just maximize accuracy would just say everyone doesn't have cancer. Because because overall it would do the best if it just said everyone doesn't have cancer because it's only misclassified 100 people. But if we give a higher weight to the people with cancer as like a punishment to our decision tree, then it'll think twice about misclassifying someone with cancer. So if you have a classification problem where your classes are severely imbalanced, you need to consider this. And how you account for that is by doing weighted decision trees. So we have a slightly unbalanced data set here where we had more people who didn't survive than survived. And so what we can do is pretty much use like a little code here to weight that. So we'll weight the people who survived higher so that if we misclassify those people, it'll be more, the algorithm will be more punished than for the people that didn't survive. And so you can see here, you can see the accuracy of people who, like this is the vanilla accuracy, is 0.84, but if we consider the weighted accuracy, it's 0.82, so it's a little bit lower. So that's important to look at as if you have an unbalanced classes. All right, so now for random forests. I mean, random forests are really an easy concept. It's called a forest because it's just a lot of trees, right? But there's why is it called random? Well, random forests are a form of a statistical process we use called bagging. And bagging is, which is bootstrap aggregating. So bootstrap is a statistical method we use if we don't have like a lot of samples. What we do is we just sample, if we don't have a lot of observations, we sample with replacement from our samples. We sample with replacement from our data. And so pretty much, say we have like 1,000 people, we'll take 100 of them and then train our algorithm on those 100 people, and then we'll put them all back, and then just randomly take another 100 people and train our algorithm on those 100 people and put them back. And so that's sampling with replacement. And by doing that, we can kind of get an overall more holistic view of our data, and it's kind of like increasing the number of observations we have without really having to go out and get more data. And so if you have a machine learning problem where you don't have a lot of samples, you should consider bagging as a process that you use. But random forest is a form of bagging because it does a decision tree, but each decision tree is based on a subset of your overall observations. And so in the case of Titanic, say there's like 1,000 people, it might take a random 100 of those people and train a decision tree on that, and then put them back in, and then take 100 people, train a decision tree on that, and put them back in. Now, why is that helpful? Well, what we'll get to in the next lesson is random forests can tend to really overfit your training, your data. And so I like to think of an example of if I went to the movies, or if I wanted to go to the movies and wanted to know what movie I should watch. If I asked one person that has watched all the same movies that I have, then they're going to have a very strong opinion, and it's going to be one person's opinion, right? So what might be a better method for me is to have 10 different friends that all have watched a different subset of the movies that I've watched. And then I get all of them to give me their recommendation of what movie I should watch, and then I just take pretty much the max poll. So I just take the max vote. And so by that way, I've kind of diversified like the tastes, right? So everyone has kind of seen like different types of movies, and so everyone will have like a slightly different opinion, right? That's why you like want a diverse team, because everyone comes from a different background, so everyone has like a different opinion. And so a random forest, by allowing each decision tree to train on different subsets of your data, they'll each kind of like learn they'll come to a different conclusion about your data. And then if you max pool all those decisions, all those predictions together, you'll get like an aggregated answer. Now, there's one other thing that, and it's called random because it just randomly picks from your observations. But there's one other thing that decision trees do. Imagine again that you have your friends. Okay, it's good that you've now decided, instead of just asking one person who's seen all the same movies as you, you've decided instead to ask a lot of friends that have seen differing movies, right? But there's one more thing you could do. You could make sure that the friends you ask all care about something different. And so maybe one friend really is your artistic friend that really cares about the art in a movie. Another friend really cares about the cinematography. Another friend really cares about like the action in a movie. So each friend cares about something different. And so you would want to ask each of those friends, because they'll all come, again, with like a different opinion, and you'll want to max pool them. So a random forest does something similar. So if we have 5 features, we'll give maybe 2 features just randomly to each decision tree. And each decision tree only has access to like 2 of those features to predict the target variable. So in the case of the Titanic data, you have all these features, right? So maybe like one friend, or one decision tree, you give the features of if they're male and what their fare is. And that decision tree has to decide, just using those features, if they survived or died, and so on to each of your friends. And you just max pool those. So we'll go over in the next lesson why that's helpful. But that's what a random forest does. And in traditional like machine learning nowadays, we don't use decision trees for prediction. We use random forests. But decision trees I still teach them because you need to know them to learn to know random forests, and they're nice for visualization. I really like visualizing a decision tree to kind of see like how my computer is thinking about my data. I think, so you had a project yesterday where you were wondering if there's a certain number of hops that the signal just drops really badly, right? So if you train a random forest, you can see, did it decide there's a certain number of hops where it decides that's the decision, and then anything over that has good signal and anything less than that has bad signal. That's that nonlinear relationship that we were talking about. So I want to show you one thing that's kind of a major cheat code, and I like it, but it's just for fun. Oh, okay, yeah. Just wanted to show you again with sklearn. It's just really easy. Instead of decision tree, you just do random forest classifier, and then you just do .fit just like before. The caveat too is you can use, they said it in the movie, but you can use decision trees and random forest not only for classification but also for regression. So even if you're trying to predict a numerical value, you can still use this method. So it's a really nice overall method. And if you saw also in the video, it can deal with missing values. So again, a really nice method. Now, we've gone over linear regression, logistic regression, decision trees, random forests. We might go over one more before we're done. But that's about like 4 or 5. And of course, there's many more machine learning algorithms out there. So in this box, you don't have to understand all of the code. It's actually not that long. But we pretty much just import every machine learning algorithm that sklearn has and just put it in a giant for loop. And just for each classifier, we're just going to fit it and then score it. And then we can actually plot the scores for all our different machine learning models. So for this particular data set, decision trees down here in score. Random forest, which we know of, is here. And those are the 2 we know about. Well, we talked about neural nets. So neural nets are here. So neural nets are doing pretty well. And each data set might have different algorithms that do really well on it. Now, this is great, and I like to just, for fun, run this piece of code on my data set. But it's kind of not the end-all in all, because for a few reasons. When you actually go to production, there's a few things you need to think about when you're picking the right model. One, we already talked about the accuracy versus interpretability trade-off. And so for your problem as a data scientist, you need to choose, is it more important for me to have an interpretable model or an accurate model? So even though Gaussian process is the most accurate model in this case, you would have to ask yourself, is it as interpretable as I need it to be? Random forests are or decision trees are very interpretable, right? And the other thing in production, especially if you're doing some live machine learning, you would really care about the time it takes. So some models, sure they're really accurate, but they take several minutes to predict, and you wouldn't want that for like a live application. So those are things you have to think about when you're picking a model. All right, well, we're going to go to project work straight away. And so for project work, you're going to use your data set and choose a categorical variable as your target, and you'll choose a few feature variables. If you don't have a target variable in your, or if you don't have a categorical variable at all in your data set, I'm not sure, oh, y'all don't. But just for training, just for learning, what you can do, and I think you had mentioned it yesterday, is you can pretty much pick a cutoff for your target variable and then just segregate it into like true or false if it's more or less than the target. So that's how you kind of make it a classification problem. So I'm not sure if I'd like recommend that for like overall, but just for learning you can do that. All right, so fit a decision tree, and you might need to do some label encoding. If you do, just ask me about it. And then print out the tree. All the code is in this notebook for you to be able to do that. Adjust the max depth and min impurity decrease so that the tree is readable. And then fit a random forest and plot the feature importance like we did in this notebook. And then make sure all your results along with your interpretation are in your final notebook that you're submitting. So that's the project for this lesson. Yeah, that's it.
And is the data set we chosen at the beginning of the class?
Yes.
Like the housing or the-
Yep.